Today on UPSC Science View, when we look around us, the clouds, the air we feel, everything comprises and forms one very important element for the Earth. Hello and welcome to UPSC Science View. Today, let's learn about the Earth's atmosphere. Earth is the only planet in the solar system with an atmosphere that can sustain life. The blanket of gases that surrounds our home planet not only contains the air that we breathe but also protects us from blasts of heat and radiation emanating from the sun. It warms the planet by day and cools it at night. The Earth's atmosphere is about 300 miles thick, but most of it is within 10 miles of the surface. Air pressure decreases with altitude. At sea level, air pressure is about 14.7 pounds per square inch, and the atmosphere is relatively dense. At 10,000 feet, the air pressure is 10 pounds per square inch, which means molecules of gas that make up the atmosphere are less dense. That makes it harder for a person to breathe and get enough oxygen to live, although there is evidence for microbial life high up in the clouds. The Earth's atmosphere is divided into 5 main layers: the Exosphere, the Thermosphere, the Mesosphere, the Stratosphere, and the Troposphere, according to NASA. The atmosphere thins out in each higher layer until the gases dissipate in space. There is no distinct boundary between the atmosphere and space, but an imaginary line about 62 miles from the surface, called the Kármán line, is usually where scientists say atmosphere meets outer space. The troposphere is the layer closest to Earth's surface. It is 4 to 12 miles thick and contains half of Earth's atmosphere. Air is warmer near the ground and gets colder high up. Nearly all the water, vapor and dust in the atmosphere are in this layer of troposphere, and that is why clouds are found here. The stratosphere is the second layer. It starts above the troposphere and ends about 31 miles above ground. Ozone is abundant here in the stratosphere, and it heats the atmosphere while also absorbing harmful radiation from the sun. The air in stratosphere is very dry, but it is about 1,000 times thinner here than it is at sea level. Because of that, this is where jet aircraft and weather balloons fly. The mesosphere starts at 31 miles and extends to 53 miles high. The top of the mesosphere, called the Mesopause, is the coldest part of Earth's atmosphere, with temperatures averaging about minus 130 degrees Fahrenheit or minus 90 degrees Celsius. This layer is hard to study. Jets and balloons don't go high enough, and satellites and space shuttles orbit too high. Scientists do know that meteors burn up in this layer. The thermosphere extends from about 56 miles to between 310 and 620 miles. Temperatures can get up to 2700 degrees Fahrenheit or 1500 Celsius at this altitude. The thermosphere is considered part of Earth's atmosphere, but air density is so low that most of this layer is what is normally thought of as outer space. In fact, this is where the space shuttles flew and where the International Space Station orbits Earth. This is also the layer where the auroras occur. Charged particles from space collide with atoms and molecules in the thermosphere, exciting them into higher states of energy. The atoms shed this excess energy by emitting photons of light, which we see as the colorful aurora borealis and aurora australis. The exosphere, the highest layer, is extremely thin and is where the atmosphere merges into outer space. It is composed of very widely dispersed particles of hydrogen and helium. Earth is able to support a wide variety of living beings because of its diverse regional climates, which range from extreme cold at the poles to tropical heat at the equator. Regional climate is defined by the University Corporation for Atmospheric Research as the average weather in a place over more than 30 years. A region's climate is often described, for example, as sunny, windy, dry, or humid. These can also be described the weather in a certain place, but while the weather can change in just a few hours, the climate changes over a longer span of time. The Earth's global climate is an average of regional climates. The global climate has cooled and warmed throughout history. Today, we are seeing unusually rapid warming. The scientific consensus, as stated by the Intergovernmental Panel of Climate Change, is that greenhouse gases in the atmosphere, which are increasing because of human activities, are trapping the heat in the atmosphere. To better understand the formation and composition of Earth, scientists sometimes compare our planet with Venus and Mars. All three of these planets are rocky in nature and are part of the inner solar system, meaning that they are in between the Sun and the asteroid belt. Venus has an almost fully carbon dioxide atmosphere, with traces of nitrogen and sulfuric acid. The planet, however, also has a runaway greenhouse effect on its surface. Spacecraft have to be heavily reinforced to survive the crushing pressure 90 times heavier than Earth, and the oven-like temperatures 872 Fahrenheit or 467 Celsius found at its surface. The clouds are so thick in Venus that the surface is invisible in visible light, because not much sun reaches the surface. This means that Venus has no significant seasonal temperature changes. Mars also has a mostly carbon dioxide atmosphere, with traces of nitrogen, argon, oxygen, carbon monoxide, and some other gases. On Mars, the atmosphere is about 100 times thinner than Earth's, a very different situation from the ancient past, when geological evidence shows that water used to flow on the surface more than 4.5 billion years ago. Scientists suggest the Martian atmosphere may have thinned over time, either because the sun stripped away the lighter molecules in the atmosphere or because a huge impact by an asteroid or comet catastrophically stripped the atmosphere. Mars undergoes temperature swings influenced by how much sunlight reaches the surface, which also affects its polar ice caps, another great influence on the atmosphere. Scientists routinely compare small rocky exoplanets to Earth, Venus, and Mars to get a better sense of their habitability. The routinely accepted definitions of habitability is that a planet is close enough to the star for liquid water to exist on its surface. Too far and the water turns icy. Too close and the water evaporates. However, habitability not only depends on the star-planet distance but also the planet's atmosphere, the star's variability, and other factors. Let's learn about the outer reaches of the Earth's atmosphere and how we can study it from NASA.
Up above the clouds, Earth's atmosphere gives way to space. This interface is called the Ionosphere. Changes in the Ionosphere, in reaction to space weather above and Earth's weather below, can disrupt communications and GPS signals and could potentially harm astronauts. So it is important to understand the region fully. Two new NASA missions, the Ionospheric Connection Explorer, or ICON, and the Global Scale Observations of the Lemon Disk, or GOLD, will work together to uncover its secrets. Together, they'll provide the most comprehensive view to date of this critical layer of Earth's upper atmosphere. ICON, from 350 miles above the planet, will home in on the effects of terrestrial weather. For a broader view, GOLD will make global-scale observations of Earth's upper atmosphere, including the ionosphere, from an altitude of 22,000 miles, gathering observations of the entire disk once every 30 minutes, more frequently than any ionospheric mission has done before. It was long thought that our dynamic sun was solely responsible for change in the ionosphere, but recent studies show that Earth's weather dynamics also play a large part. Weather such as hurricanes and wind patterns near the planet's surface can influence both the atmosphere and the ionosphere. Mission scientists want to understand how weather phenomena affect the upper atmosphere and the nearest reaches of space. Scott England, ICON project scientist at Virginia Tech, explains, "We know Earth's ionosphere varies by an extraordinary amount from hour to hour and day to day, but we don't know the cause of much of this variability. ICON focuses on trying to understand if weather near Earth's surface can explain any of the changes we see in the ionosphere." ICON, which is planned to launch in 2018, will fly through the upper atmosphere, gathering information of the space it travels through as well as observing the lower ionosphere from a distance. It will investigate properties of charged particles in the ionosphere and of neutral atmospheric particles, such as those shaped by weather far below, to determine how they interact. GOLD launched on January 25, 2018 aboard SES-14, a commercial communication satellite, and is the first experiment that can track hour-to-hour changes in the ionosphere. GOLD is flying on a geostationary satellite to image the ionosphere from a distance, similar to how weather satellites provide global-scale images of the Earth's lower atmosphere and surface. England says, GOLD will provide the context we need to separate what changes as a spacecraft moves from region to region from what is really changing with time. He continues, much like how we might study a hurricane through a combination of a weather satellite that can track its progress and an airplane that can capture up-close measurements, we can use ICON and GOLD to provide both the detailed and global scale views of what is happening in our upper atmosphere and ionosphere.
Thank you very much for listening to this discussion on the Earth's atmosphere. For more such discussions, get the UPSC Practice app from the App Store.